Welcome to qnawire.
Looking at how activity, or the rate at which decay occurs, changes over time for a given isotope, we can make predictions about the age of different things. The equation that we use is the activity at any given time is equal to the initial activity times 1/2 T over T 1/2, where T is the time or the age and T 1/2 is the half-life. So we look at the activity at a given time. The initial activity the time that's gone by, or in this case, the age, and the half-life, which is specific to the isotope. So typically we use carbon-14 for archaeological dating. And so with carbon-14, the initial activity is 15.3 decays per minute per gram. And the half-life is 5,730 years. So if we have, for example, an artifact part, which in this case is the handle of a sword, that has an activity of 10.1 decays per minute per gram, we can solve for the age. 10.1 equals 15.3 times 1/2 T divided by 5,730 years. Dividing both sides by 15.3, this is 0.6601. Because the T is in the exponent, we have to take the natural log of both sides. So the natural log of 0.6601 equals the natural log of 1/2 times T over 5,730. Dividing both sides by the natural log of 1/2. Point 599 is equal to T over 5,730, or cross multiplying, T is 3,433 years old. We do the same thing for the wood, which has an activity of 13.8 decays per gram per minute. So 13.8 equals 15.3 times 1/2 T to the 5,730. Same steps. Dividing by 15.3, 0.90196 equals 1/2 T to the 5,730. Taking the natural log of both sides. And then solving algebraically, T is 853 years old. The third is a sample that has an activity of 12.1. So 12.1 equals 15.3 times 1/2 t over 5,730. Using the algebraic steps above, we find that t is 1,1940 years old. And then finally, the sheath has an of 15.0. So our initial activity again is 15.3 times 1/2 t over 5,730. T equals 163 years ago. And so if we look at which is closest to 100 AD, or almost 1900 years ago, that would be the ribbon.